Hello, dear students. Welcome to the channel and very welcome to this playlist in which we are discussing the symmetrical fault analysis. Up till now, we have discussed about transient on transmission line. We saw the series RL circuit. Then we saw the short circuit current analysis of synchronous motor or synchronous generator, basically the synchronous machine on no load, and then we saw the same for the on load conditions. And in the very last lecture we also did the fault calculation using Z bus equivalent circuit. So today we are going to discuss how can we select a circuit breaker for my system. So if you and we also going to discuss about the selection of my Z-bus algorithm based on short circuit studies. So for that we will need the we will require knowledge of fault current using Z-bus equivalent circuit. So if you haven't checked out the previous video, the link will be on the top right hand side corner of your screen. It will be flashing on the I button, so you can click on it and you can see it. If you have already seen it, let's move further and see how can we select the circuit breaker. So any circuit breaker of system is the requirement which can satisfy few of very important requirements or conditions. So the first among them is to make or break the whole circuit. Either we can do it manually or you can use any remote control operation in normal conditions, and you can do the same in the fault conditions as well. So basically you can make or break your circuit either manually or remote using remote control. uh, you can also do the same. You can break the circuit automatically as well under any faulty conditions. And if you want to do it manually, if you want to make the circuit uh, either manually or remote using a remote control operation under the fault conditions, you can do that as well. So basically its work is to either make or break your circuit uh, despite considering the conditions of your network. If there is a we are having fault condition, then it will break the circuit, otherwise it will make the circuit. So depending on the situation, it will act and either make or break your circuit. That's the basic funda of circuit breaker. So when fault occurs, what happens? The protective devices will get activated, right? So there is a time difference between determination of my overcurrent in my circuit, by which the current which is detected by my protective relay, and the other initial trip command, right? First, what will relay do? It will detect the fault and then only it will give the trip command, right? So there is time difference between those two, and this time difference is known as detection time, right? So that is something called detection time. Where did we were discussing, okay, this one. So it is called detection time, as I've mentioned here. And then the context of my circuit breaker will be held together by one mechanism, such spring mechanism. And when the trip commands will be the trip command will be given, the spring mechanism will be released, and spring mechanism will release the contactors, right? So spring mechanism will release the contacts, and the contact will be set free. So when this such two current carrying contacts part ways, there will be a voltage which will be initiated at the contacts, right? and a large voltage gradient will appear in the medium between two contacts. So this voltage gradient will be ionized in the medium, and because of that, it will maintain the current flow, and this current will generate extreme heat and so much light. So we call this gradient electric arc. Okay, so the arc you see in the circuit breaker is basically a voltage gradient. And for different mechanisms, we use different types of circuit breakers. We use different mechanism for cooling and extinguishing cooling and extinguishing operation. And because of that, what circuit breaker has to do, it has to withstand the fault current from instant of initiation, because when initiation is getting taking place, which means it has only detected relay has only detected my fault. It is not actually working on towards the solution of the fault, right? So it will it have what somebody has to withstand that current. Who will withstand this current? So my circuit breaker will withstand such current, and it will withstand from the instant of the initiation of fault till when? Till the time of the arc is getting extinguished. So in that time period, circuit breaker has to withstand the fault current, and that you can see here. This is the detection time from the occurrence of fault till initiation of trip command. You can see the detection time, and from the initiation of trip command till the arc extinguishing, this is the interrupting time in which the circuit breaker is withstanding the fault current, right? So contacts are parting in this part, interrupting time part. Okay, so what are the major duties for circuit breaker? So the major duties which are imposed on my circuit breaker when in the faulty condition on system, what will be it? If there is a fault on the system, it will get connected, right? So we all know that three phase faults are very scare, right? Because they are very less in numbers, but they will give you the maximum short circuit MVA. And for selection of circuit breaker, for the selection of circuit breaker, the maximum possible short circuit MVA to be interrupted with respect to type of fault, its location and generating capacity is to be found. And as it is essential for circuit breaker to be capable to interrupt it, so two major factors are there which are utmost important for the selection of circuit breaker. I've mentioned both of them here. The first one is the maximum instantaneous current that a breaker must withstand, right? So uh, we already talked about it, so I'm not talking about it in detail one more time, because we have already talked about the maximum instantaneous current which breaker must withstand. The second one is the total current when the breaker contacts part. Okay, so the total current when the breaker contact parts. So what happens in the high powered circuit breakers? When you want to do the selection for high power circuit breakers, the subtransient current is multiplied by the factor of 1.6, right? Why? Because we need to determine the RMS value of the current in the circuit breaker, right? So you must know what is the maximum value that your circuit breaker must withstand in order to sustain the damage. And this current, we call this current momentary current. Now except for this momentary current, there is one more current called interrupting current. So the interrupting current of circuit breaker will be lower than the momentary current, and it will depend upon the speed of my circuit breaker, right? So uh, it may or may not be asymmetrical, because there is some DC component which will still continue to decay, and because of that it can be asymmetrical. But basically what happens, uh, if my circuit breaker has so many number of cycles, like if my circuit breaker is having 8 cycles or even slower than that, then I will be multiplying by only one factor. Now let's reduce the number of cycles. If my circuit breaker is having 5 cycles, then I will multiply with 1.1 as multiplication factor. If my circuit breaker is having 3 cycles, then I have to multiply with 1.2. If my circuit breaker is having just 2 cycles, I will be multiplying with 1.4. Now the breakers are usually classified by their nominal voltages. um, I have mentioned all the factors affecting that classification of my breaker. So it can be classified by their nominal voltage. You can take continuous current rating, you can consider maximum rated voltage, you can consider the K factor, you can consider the rated short circuit current at maximum voltage, and operating time is also most important aspect while you classify your circuit breaker or decide your circuit breaker. Now I've mentioned about K factor. So what is K factor? So basically K factor is just a ratio. It is ratio of rated maximum voltage to the lower limit of the range of your operating voltage. So the maximum symmetrical interrupting current of my circuit breaker will be given by K times the rated short circuit current. Okay. So that was your selection of circuit breaker, and now we will move forward and we will discuss the Z bus formation. So basically for the Z bus formation, basically what do we use? We use uh, Y bus. We basically invert my Y bus and we find the Z bus. So whatever load flow computation we normally do with the help of admittance bus matrix will be helpful, right? So all the calculations related to load flow computation will be done by bus admittance matrix. But um, this is the short circuit studies we are talking about, right? So for the short circuit studies and the calculation of the faults, we use bus impedance matrix or Z bus matrix. And why is that? Because in short circuit studies, what happens, all three sequence components and sequence networks will be involved, and a direct solution is possible, and iterations will be there will be no need for any iterations, right? They are out of scope. So we use this Z bus or Z bus transformation. Now how do you create this Z bus? So first, the symmetrical fault current at any bus in power system can be easily obtained from your bus impedance matrix, right? And it is required that your Z bus should be obtained by the inversion of your admittance bus or Y bus. So what do? We do nothing new. We simply take our Y bus. So this is the Y bus I'm taking. It is 3 by 3 Y bus. Y11, Y12, Y13 to Y33 are my components, and I'm doing nothing new. I'm simply inverting my Y bus matrix and I'm creating my Z bus matrix. So I will have Z11, Z12, Z13, Z21, Z22, Z23. I'm just simply inverting my Y bus matrix and I'm getting Z bus matrix. Now the symmetrical fault current at any bus, let's say bus 1, we can give it by 1 divided by Z11 for bus 1, right? And the values we will be considering here will be per unit values. So 1 by Z11 per unit. Okay. Same ways, if I want to find the same symmetrical fault current at bus 2 and bus 3, so I will be having 1 divided by Z12 per unit and 1 divided by Z33 per unit for bus 3, right? Why? Because we are taking the bus voltage as 1 per unit as a default, and that is why we are getting the value of our impedances in 1 division by Z11 per unit. Okay. And also that is also the pre-fault value of voltages, right, for the buses. Now for the large system, what will happen, this method will be not very feasible. Why? Because the inversion of very large matrix is very difficult. The other thing that if you want to do any change in your network, the full whole matrix will be affected, right? So you need to build the whole matrix one more time, and one more time you need to do the whole inversion thing. So that is not convenient at all. You have to do so many changes just because of small change in one of your admittances or impedances, right? So what we can do, we can use the algorithms. There are four different modification techniques, so we will use them. Now the because right now we are talking about the determination of my matrix, so the determination of fault current by formulating impedance matrix can be done using my network theory. The network theory, same network theory we talked about last in the last class, right? So how do we form this passive linear bus network? So we can form it by this. On the left hand side I have taken voltages v1 v2 up to vn. On the right hand side I have taken the multiplication of two buses, z bus and I bus. Z bus is containing n cross 1 impedance values, and I bus is containing, sorry, Z bus is containing n cross n impedance values, bus impedance, and I bus is containing n cross 1 current values, which we collectively called current bus. Now if you want to find the Z bus value or element value of some particular element of Z bus, you can find using this formula given below here. Zik is equals to vi divided by ik. So I think that is pretty much self-explanatory when I is equals to 1 I1 I2 up to in equal to 0, but ik does not equals to 0. If your ik will be 0, that means, what does it means? That means your impedance will be infinity, which is not practically possible. And if that happens, that if there is no current, if ik is infinity, that means your circuit is not making any sense as well, correct? Now let's see how we can build algorithms for short circuit studies. So uh, we can create an algorithm, we can describe the algorithm in terms of modification in existing impedance matrix bus with new modification as well, with new impedance matrix. So we will do nothing, but we will make small changes in most for the most of the time we will make small changes in the last row and last column, and by doing that we will find the different modification matrices. Okay, so when a new element which has your self impedance as some, let's say zs, or z for instance, let's say z is added to my bus, what will happen? We can create there is possibility of creation of new bus, right? If my element is a tree branch, then new bus. If it is not a tree branch, if new element is in the link, then new bus may not be created. But the point is, uh, in each of the cases we can find new bus, and we can classify them using this four analogies. First one says we can add a new z bus from a new bus to a reference bus. And if you don't get this analogies, no worries, I will show you the diagram, and from that you will get it, so no issue there. Second one says we can add a z bus from a new bus to an old bus. The third one says that we can add a z bus from an old bus to the reference bus. And the fourth one says we can add a new bus between two old buses. That's interesting, isn't it? Here's the type 1 modification. So as I've told you, this is the diagram, and by seeing this diagram now you might have understood what I meant by adding a new bus to your reference bus. So we are having various number of buses till 1 to n, and the last bus is my reference bus, and we are adding a new impedance to my reference bus here. Okay, so um, this is my new bus q, and this is my impedance zs. So this zs is connected between the reference bus and my new bus, right? Q is new bus and the last bus was a reference bus, as I've told you. So based on that, if I want to find the value of vq, can you tell me what will be the value of vq, the voltage across this bus, new bus? Because the reference bus is 0, then vq will be zs into iq. Simple. Now the complete set of equation will become something like this. The whole thing will stay same, but a vq will be added in the last, because we added a new bus in the we added a new bus, so it will have potential vq, and so we added it. Then we will have impedances z11, z12, z1n, and it will go till the last bus. The last bus's last row will be 0, the last column's last row will also be 0. So the last element of my first column will be 0 row wise. The last elements of my last column will be 0 again, right? And the only value which will have the which will hold some value will be the value which was present in the diagonal. It will hold value zs. And in my current matrix, new current iq will be added, just like new voltage vq was added. So the addition of new branch will be implying the addition of n plus 1th row and n plus 1th column, and based on that we will get ziq is equals to zqi is equals to 0. So what did we took? We took I is equals to 1 2 3 up to n, and we put the value of n is equals to iq is equals to 0. So the whole last column and last row went 0, and the value of zqqq will be zs. So we got the value of zs, right? Same way is what we will do. We will let's see the type 2 modification. In the top type 2 modification, what is happening? We took the second modification, and what did we do here? We added zs from new bus to an old bus. So we are having zs from a new bus to an old bus. The here you have uh, 1 2 up to n buses. Then this is a new bus we are adding, the bus k, and we are adding an impedance in it. We are adding an impedance zs in it. Okay, so we are adding zs after adding a new bus k. So that is my second modification, type 2 modification. In this modification, what will happen? My final matrix will look something like this. Because we added kth bus at last, we will get v1 up to vn, and again we added impedance, so we will get vq. This time what will happen? I will get values in the last column and last row. The values will be same values which were present in the values will be given to the matrix the same way we gave earlier. So the values will be z1k, z2k, z3k up to z nk. And same ways that was for column. For the row what will happen? k1, zk2 up to z nn. The value will remain same. The last value will be zkk, because that was the value of diagonal value, plus zs. Okay, zkk, which was the value of diagonal value, plus zs, which is the new impedance which has been added to my uh, which has been added to my new bus. So we take addition of both of them in the value of diagonal value of my last column and row. Current value, same thing will happen, it will remain unchanged. Only change will be the addition of iq. Except for that, everything else will remain same. After that, let's see the type 3 modification. So again, as I've said, in type 3 modification, what was happening, addition of new link zs was taking place between the old bus and the reference bus. Okay, so this kth bus is an old bus and this is my reference bus, and we are adding this zs bus or zs impedance or zs link between both of them. So what will happen in this case, z will be connected between new bus and old bus, and because of that, new bus will be connected to the reference bus. So in that case, what will happen when my new bus will be connected to the reference bus, so its voltage will come to 0. So here you can see the voltage has came to 0, right? And uh, the rest of the voltage will remain same, but because my old bus, which is connected to the reference bus via zs link, so because of that my voltage will become 0. The remaining part will remain as it is in as it is as the second type modification. And for I, we will have new added value iq for my qth for my qth bus, right? Now if iq will be eliminated from this equation, what will happen, the last row and the last column of impedance matrix also will get eliminated because voltage is 0 already. So how will the z bus look like? It will look like something like this: z bus new will be equals to z bus old, which was the value initially we stated, minus z I minus 1 by z kk plus zs, and in the bracket my z bus mentioned. uh, Here, please don't get confused, here I have mentioned them separately. I first mentioned the columns, then mentioned the rows. There are no two different z buses. Okay, now let's come to the type 4 modifications. This is the circuit for type 4 modification, and it is plain and simple. We are adding a new link between two old buses I and k, as you can see here. So here what will happen, same thing will happen which happened previously. So again, because it is getting added between two a new link is added between two existing buses, the value of last bus will become 0, the value of voltage at last bus will become 0, and because of that, uh, the last column and last row will change. How it will change? It will be it will go from z minus 1 minus z1k, zik, or z1i minus z1k, z2i minus z2k, and up to it will come till zs plus zi1 plus zkk minus 2 zik. Current matrix will remain as it is. Again, the only thing which will come here will be iq. Remaining part will be the same, and you can represent your new z bus using this formula. Again, this thing is same as I represented in the type 3 modification. So that was your all four types of modifications which can be used in case of fault occurrence. And that was the wrap for symmetrical fault analysis. Now we are going to discuss about the symmetrical components, but before that, let's see one numerical so that you can finish it easily. So the question is, we have three phase 5000 kVA 11 kV alternator. It has subtransient reactance 8%, and three-way short circuit current is occurring at its terminal. So we have been asked to determine the fault current and the fault MVA. So now alternator's percentage reactance is based on its own voltage and kVA ratings, as we already know. So we can find the value of base current from this formula: base kVA divided by root 3 into base kV. Basic formula, no explanation needed in this formula. You already are familiar with this formula. You can determine the current from it. So base kVA is given 5000, so we will write 5000 root 3 as it is. Base kV is given 11, so we will put it over here, and we will find IB, which is our base current. Now we will find the per unit fault current. So in order to find the per unit fault current, you either need base current and base current and present current value, or you can divide the per unit voltage with your per unit reactance, and you can find the per unit value of your fault current. So we will divide the per unit voltage by per unit reactance. Per unit voltage, we will take 1, and per unit reactance we have been given 8%, so we will take 0.08. Based on that, we can find my per unit fault current, which will be 12.5 angle minus 90 degree. Because of reactance, we are considering reactance here, so the angle will be minus 90 degree because it is pure reactance. Now we will calculate the fault current. So it will be the short circuit current, per unit value of short circuit current into IB, right? So you already are aware of both of them. We already calculated the IB 162.5 in the previous slide. See here. And for the value of ISC, we determined it just a minute ago, 12.5. So you can find the fault current ISC, which will come 3281.25 amperes. Now for the fault MVA, so it is basically to find fault MVA, what do we do? Root 3 short circuit current into short circuit voltage, or source voltage, basically, not short circuit voltage, sorry. So root 3 ISC into VS. So you know the value of ISC, you know the value of VS, so you can find the fault MVA, which is 62.5 MVA. So that's the wrap for the chapter. I will be seeing you with the next video, in which we will be discussing not unsymmetrical fault. We will be discussing symmetrical components. So if you have any doubts related to this chapter or any other chapter, if you have any queries, you can mention them in the comment section below. If you have any feedback related to channel, every feedback is welcome. I will try to reply you as soon as possible, as quick as possible, and as much as possible. So until next time, thank you very much for listening, and goodbye.